For my project, I'm going to be discussing electrical engineering and how it uses multivariable calculus. For starters, what is electrical engineering? It is defined as the branch of engineering concerning the study, design, and application of devices that use electricity, electronics, and electromagnetism, so anything related to circuits and modern technology. Top schools in the U.S. to study electrical engineering are MIT, UC Berkeley, Stanford, Georgia Tech, University of Illinois Urbana-Champaign, Carnegie Mellon, and Caltech. The one that is considered the top in the U.S. is MIT, and that is mainly because of their low student-to-staff ratio, meaning more personal interaction between the two, award-winning robotics team, and the abundance of research centers on campus. Average starting salary is $64,936. Average annual is $101,600, and the top 10% earn $153,240. For the most part, engineers work in offices in design, telecommunications, and research and development. However, if they need to look at a specific problem or piece of equipment, they can find themselves at a production plant. They can also find themselves at a research facility. Now the most important question. How does electrical engineering use multivariable calculus? There is one set of equations that is used often in electrical engineering and electromagnetism, the Maxwell Equations. They're named after physicist James Maxwell, and there are a set of partial differential equations that describe the electric and magnetic fields that arise from distributions of electric charge and currents, and how those fields change over time. There are 4 equations in their differential form: Gauss's law for magnetism, Faraday's law, and Ampere's law. For this presentation, we'll focus on the application of Faraday's law in electrical engineering. Faraday's law shows that a changing magnetic field within a loop causes an electric current to be induced. In mathematical terms, the equation indicates that the greater the change in the magnetic field over time, the greater the curl of the electric field, and thus a greater current is induced. Before we move on to applications, I want to explain exactly what the curl operator is and what it means. The curl operator is a type of vector operator that describes the curl of vectors in a vector field. It is found similarly to how a regular cross product is found, except the top row of the matrix has the partial derivative operators for each variable, and the bottom row has the I, j, k values of the original vector in their designated column. Performing the cross product using this matrix leaves you with this vector. Now take a vector field, where each point is assigned a magnitude and direction. If there is a curl of vectors at any point in the field, where the vectors literally curl up into a little circle, the vector found with the curl operator is the vector normal to this curl. The magnitude of the vector indicates the degree of the curl, so a vector with greater magnitude indicates a very curly vector field. The curl, in the context of Faraday's law, represents the current flowing through a loop, with a greater curl with greater magnitude indicating a greater current. Thus, if the partial derivative of the magnetic field with respect to time is greater, the curl of the electric field is greater, which means a current is induced due to the change in magnetic field. How do electrical engineers use Faraday's law? Faraday's law lays out the groundwork for electromagnetic induction, which is the creation of a voltage or electromotive force using varying magnetic fields. The concept of electromagnetic induction is used in devices such as electric generators, induction motors, transformers, current lamps, and inductors, all important components for building, designing, and powering other devices. The equation itself can be used to calculate the degree of curl given a certain change in time in the magnetic field, which can then be used to predict/determine current running through a circuit, leading to an easy calculation of voltage or any other property of a circuit. Now the final question is, am I interested in pursuing it? The short answer is no. I'm not particularly interested in the design of electronic devices and circuits. I rather work on programming/using them.